Welcome back, everybody. Welcome to part 2 of section 5.3, Matrices for Linear Transformations. Okay, so before we get started with this all-important second part to the section 5.3, I want to recap for you 5.3 part 1. Okay, so if you haven't viewed the video for part 1, this recap is not going to be enough for you. If you haven't viewed the video for part 1, get out of this video and watch the video for part 1, and then attempt to look at part 2. Okay, in any case, here's our recap for part 1. First of all, we started out with the idea that every linear transformation from Rn to Rm, so between two vector spaces of just column vectors of real numbers, every linear transformation from Rn to Rm can be written as a matrix transformation. That means we can find some m by n matrix such that T takes something in Rn, T of x equals that matrix times x. Okay, then we got we looked at the big idea for section 5.3. The big idea is that every linear transformation from Rn or Rm to wherever, or not even including Rm or Rn, every linear transformation between two vector spaces V and W can, in some sense, be computed using matrices. Now, before we look at the next line, just imagine, though, that the vector spaces V and W don't have to have anything to do with matrices at all. Okay, but computations of the value of the linear transformation at vectors from V can somehow be computed using matrices. This is a really, really big idea. Okay, so then we started going into the details. Suppose that V has a basis alpha consisting of vectors alpha, v1 through vn, and that beta vectors w1 through wm is a basis for w. And once again, v and w don't have to be related to each other at all, at least in appearance. The vectors in V don't have to look anything like the vectors in W. Okay, the vectors in V could be points in R2, and the vectors in W could be trig functions. I just made that up, okay? So, okay. Then, if we pick something out of V, it would be sort of like taking for the linear transformation, it's a matrix transformation, taking a vector x from Rn and finding T of x. If we take a vector V out of the vector space capital V, then we get the similar result that we got for matrix transformations. Then the coordinates, not the actual value of T of V, but the coordinates of T of V, those are just real numbers, scalars. The coordinate vector of T of V is equal to some matrix T times the coordinate vector of V relative to the basis beta. It looks very similar to T of x equals AX. Okay, but again, we're not computing the actual T of V. We're just looking at computing the coordinate vector of T of V relative to the basis beta, often in vector space W. Okay, so what did we call that vector T with subscript alpha and superscript beta? We called it the matrix of T with respect to bases alpha and beta. Very often, the vector spaces V and W are the same, and we're looking at a linear transformation that operates within a single vector space V. Okay, so its vector space would be from V into V. We call that a linear operator. And in that case, we might have the two bases the same. So if alpha and beta are the same, then we call that matrix T the matrix of T with respect to alpha. So we don't have to say the matrix of T with respect to alpha, the bases alpha and alpha. Okay. Then we got into rather ominous discussion of how to form the matrix of T with respect to the bases alpha and beta. And it's not a simple matter. Lots and lots of computation had to take place. So I tried to color code things to keep things sort of simple. The first thing we do is we take the basis vectors in alpha and look at the action of the linear transformation on those basis vectors. We find T of v1, T of v2, up to T of vn. Then when we found those things, we take those numbers in the range, those vectors in the range, T of v1 through T of vn, and we write them in terms of the basis vectors in W. Now remember, in W we had the basis vectors W1 to Wm. So we would take T of v1, and then we would somehow write that as a linear combination of the W's. We take T of v2 and do the same thing all the way up to T of vn and find T of vn in terms of the basis vectors in W. And that's not easy. That's not an easy task. Well, it's a potentially very tedious task. Once we find those numbers, we take the coefficients of those vectors, T of v1 through T of vn, just the coefficients, just the a sub ij's, and we put them as columns in a matrix. Okay, in the same order that we found T of v1 to T of vn. When we do that, we have found the matrix of T with respect to the bases alpha and beta. And there's a lot of work going into finding those A values for this M by N matrix. So in general, it's very labor intensive to find the matrix of T with respect to bases alpha and beta. Okay, at this point it would have been it's a good idea that you have looked at some homework problems on this, so you're kind of familiar with the mechanics of finding these subscripted values for this matrix. In any case, a restatement of the problem, unless we're finding the matrix of T with respect to alpha, where alpha is a real simple standard basis, unless we're finding that, and we saw that in our example in the last video segment, the matrices, the matrix of T with respect to alpha and bases alpha and beta, or simply the matrix of T with respect to the basis beta, can be difficult to find. So now we start our task for part 2. We would like a way to find this potentially or one of these two potentially difficult matrices, the matrix, let's say the matrix of T with respect to let's say the difficult basis beta, by using that easy to find matrix of T with respect to alpha. And that's where we are. I'm going to give you a really nice visual on how this is going to work. I mean, this is amazing. I'm surprised that the author of your textbook didn't do this. I did not invent this visual. I found this visual online. I wasn't aware of this visual prior to a couple of years ago, but apparently it's a big deal in linear algebra courses as of a few years ago at least. Okay, maybe it's really old. I don't know. Okay, so here's the main idea. Here's a visual on the main idea, and again, this is priceless. I think this is priceless. Main idea. Okay, so for the remainder of our lecture, we're going to be looking at a linear operator. So we're going to assume that T is a transformation that goes from V into V. Okay, so we're looking at a linear operator. Again, our linear transformation is from V into itself. So we're not looking at V into one vector space V into an entirely different one, W, for the remainder of our video lecture. So here goes this really great visual. So let's see if I can make it now that I've got this pressure on me to make it look great. Let's see. Here's the vector space V. And suppose we, within that vector space, have a basis beta. Okay? I'm just making sure that the video is rolling here. Okay. And within that vector space V, suppose we find the coordinates of a typical vector in V with respect to beta. Okay. Our goal is to come up with the matrix of T with respect to beta. Our initial goal is to come up with the matrix of T with respect to beta to figure out the coordinates of T of V. Okay? And the coordinates of T of V we'll put over here. This is still the vector space V. Remember, we're working within one vector space. So what we would do if we were doing this directly, we would, that is using the portion of the first part one of this video segment, we would find that the coordinates of T of V with respect to the basis beta equal the matrix of T with respect to the basis beta times the coordinate vector of V relative to the basis beta. Now, there's no real problem with that, except that this matrix, the matrix of T with respect to beta, can be difficult to find. So let's write this as this matrix within the big arrow is difficult, I'll put it in quotes here, to find. By difficult, I mean labor intensive for us. Okay, so this is where we are so far. I want to take an alternate path to get the coordinates of T of V with respect to beta. I'm still after the coordinates of T of V with respect to beta. That's not going to change in this problem. But I'm going to take a different path. I'm going to start with the coordinate vector of V relative to the basis beta, the same thing I started out with. But I'm going to come up with a magic matrix, and it's really not a magic matrix, but I'm going to call it that. I'm going to come up with a matrix that changes the basis of coordinate vectors from beta to, let's say, an easy basis alpha. Okay, don't worry if you're not with me. This will all come out real well. Okay, so I'm going to go this way instead. Okay, so bear with me. I have to draw slowly here because I can't draw. So here's a matrix P. I have to come up with this magic matrix P that changes the coordinate vector of V with respect to beta to the coordinates of the same vector with respect to an easy basis alpha. Okay, so how does that magic matrix work? Well, if I take the coordinate vector of V relative to the basis beta and I multiply it P times that magic matrix converts the coordinate vector of V with respect to beta to the coordinate vector of V with respect to alpha. Okay, so now I'm up here meaning in the same vector space, but the basis is now the simple basis. We can even consider it the standard basis if you want, but it doesn't have to be the standard basis. The simple basis alpha, and we will have the coordinate vector of v with respect to the simple basis alpha, and that's going to equal capital P times what we started out with, the coordinate vector of v relative to the basis beta. Okay, it's that P that's at that matrix P, and it's an n by n matrix. It's a square matrix. It's that P that it's the object of our affection. It's our goal to define and to see how it forms. We're not there yet, though. Remember, the goal is still here in the lower right hand corner. I want the coordinates of T of v with respect to the basis B. Okay. Now remember what was easy to find. What was easy to find, it was the matrix of T with respect to alpha. Okay, so now all three of these boxes so far, they're the same vector space. Okay, we're just looking at different bases in these vector spaces. We're now assuming that I have that same vector v in terms of the alpha basis, and I have this vector, this matrix of T with respect to alpha at my disposal, which was easy, in quotes, to find. Okay? So if I multiply that easy matrix of T with respect to alpha times the coordinates of v with respect to alpha that I got with that magic matrix P, then I will have the coordinates of T of v with respect to alpha by our work last time. That's nothing more than the matrix of T, this is what we did last time, with respect to alpha, which was easy to find, times the transformed coordinate vector of v relative to the basis alpha. Okay, well, we're still not there. I have the coordinates of T of v. Remember, that's what my goal was, to find the coordinates of T of v, but not with respect to the easy basis. I wanted the coordinates with respect to the complicated basis. And you're thinking, why didn't I just go directly? Because that matrix of T with respect to beta was difficult to find. So I now have the coordinates of T of v with respect to alpha. Okay, and what does that equal? It equals the matrix of T with respect to alpha, and I'm going to substitute what I had in the last picture. The coordinates of v with respect to the coordinate vector of v with respect to alpha is nothing more than P, the magic matrix, times the coordinates of v with respect to beta. Okay, but that's not what I want. I want the coordinates of T of v with respect to beta. Now here's the deal. The magic matrix changed from basis beta to basis alpha. I want a magic matrix that converts back from the basis alpha back to the basis beta. What do you think that matrix is going to be? It's actually right here in all this, if you really think about it. If by multiplying by P, I convert the coordinates of a vector from beta to alpha, how do you suppose I can convert back? If I multiply by the inverse, that should change the basis back to beta. Change. Let's see. Back to basis beta. So that should produce what I'm looking for. The coordinates of t of v with respect to beta then should be, well, let's do it. It should be P inverse times the coordinates of t with respect to t of v, rather, the coordinates of t of v with respect to alpha. But we saw or see right above that that's that complicated looking matrix of t with respect to alpha times p times the coordinates of v, vector of v with respect to beta. Okay. Now it looks like this roundabout trip is a lot more complicated, but look at the net result here. Our goal was to compute the coordinates of t of v with respect to beta, and the direct trip would have said we multiply the matrix of t with respect to beta times the coordinate vector of v relative to beta. Now notice that this P inverse times the matrix of t with respect to alpha times p, that's what we're multiplying by the coordinate vector of v with respect or relative to the basis beta. Compare the position of these two matrices, and we have the main result in the last part of our section of our section 5.3. Concentrate on the little green up and down arrow there. The big result for part 2 is that the matrix of t with respect to beta, that complicated thing, is nothing more than the inverse of this magical matrix, which converts from beta to alpha, basis beta to alpha, the inverse of that matrix, times the simple to find matrix of t with respect to alpha times the matrix P. This is the big result. This is what we're headed toward. Now the problem is right now is we need that magical matrix. So basically we're going to spend the rest of the video lecture developing that magic matrix. It turns out it's not that difficult to construct. Okay. So let's say there's our main goal where, I don't want to go to green here, I want to stay black, where P changes basis from beta to alpha. The coordinates of v with respect to alpha equal P times the coordinates of v with respect to beta, the first arrow going up. Okay. So if you want the coordinates of v with respect to alpha, multiply P times the coordinates of v with respect to beta. So P inverse converts from where to where. We said it already. We're just sort of reviewing before we dig in. If P changes basis from beta to alpha, P inverse changes from alpha to beta. How is that possible? Multiply both sides of this last equation by P inverse. Multiply both sides by P inverse. Okay, and what happens? P, V, beta. All I did is I slipped in multiplication on the left on both sides. I get P inverse times the coordinate vector of V relative to the basis alpha. P inverse times P is the identity matrix. And look, I get the coordinates of V. Read this backwards. The coordinate vector of V with respect to or relative to the basis beta equals the P inverse times the coordinate vector with respect to alpha. This converts back to beta. It goes from alpha to beta. Okay, so let's talk about P, the matrix that converts from beta to alpha. Okay, we start with some bad news. And it's just a psychological thing. This matrix P converts from basis beta to alpha. The author of your textbook calls it something very bad. The author of our textbook, calls P. You're not going to like this. I find it unnerving. He calls it this. Let's see. What does he call it? I would need to be real precise about this. He calls it the change of basis matrix from alpha to beta. And it does not convert from alpha to beta. It converts from beta to alpha. And I don't know why he calls it the change of basis matrix from alpha to beta when it converts from beta to alpha. So with that, we just have to get used to it. I don't want to change the name of this matrix. In case you end up studying the textbook, I want us to be consistent with what he calls this matrix. Okay, he uses it to convert also, just same as we're going to do, to convert from beta to alpha, but he calls it from alpha to beta. Okay. All right, so let's develop this matrix once we can get past its poorly named name. So here's an example. Here's a simple example to show you how we compute this change of basis matrix. Okay, so let's do this. Let V, the vector space, equal P1, the set of all polynomials of degree 1 or 0. Okay, and let's consider the basis alpha as a standard basis, x and 1. And let's consider basis beta consisting of 4x minus 1, and let's say negative 3x plus 1. So just as a reminder, what's going on here? we're working with P1. So here's the vector space P1, and we're looking for a matrix, a 2x2 matrix that works within P1. So we're not looking at a linear transformation. We're looking at a matrix that works within the same vector space. Okay, so in P1 we have a basis beta. Also in P1 we have the basis, this nice basis, simple basis, alpha. And that matrix that we're looking for, P, all it does is it takes the coordinates of a vector, the coordinate vector of V with respect to beta, or relative to the basis beta, and converts it to the coordinates of a vector in P1 with relative to or respect to alpha, just by multiplying P times that coordinate vector. So what I haven't given you is how to find that P. Here it is. What we do is very similar to how we find the matrix of T with respect to bases alpha and beta. What we do, and this is the key here, so I'll write it in yellow, I guess, is we'll write the vectors in beta in terms of the vectors in alpha. We've done this if the words don't make sense. You take, let's say, the first beta vector, 4x minus 1, and you write it as a linear combination of the vectors in alpha. This is 4 times x plus negative 1 times 1. So there are the vectors from alpha. You do the same thing with the second basis vector. Negative 3x plus 1 is nothing more than negative 3 times x plus 1 times the second basis vector at alpha. Okay, and here's p. P is the vector whose columns are 4 and negative 1. They're the coordinates of the basis vectors in beta relative to the basis vectors in alpha. So 4, negative 1 is very, very similar to what we did with the matrix of T with respect to the bases alpha and beta. Okay, this matrix changes the coordinates of a vector, a v, from the vector space P1 from basis beta to alpha. I want you to see that. I want you to see that actually done. So let's pick something out of P1. Let's let v equal 27W1 plus 34W2, where W1 and W2 are the basis beta vectors. So W1 is 4x minus 1, and W2 is negative 3x plus 1. Okay, so what are the coordinates of v with respect to beta? Well, I'm sorry, what is the coordinate vector of v relative to the basis beta? It's just the column vector 27 and 34. Okay, no mystery there. Now, let's compute p times the coordinate vector of v relative to the basis beta. This is nothing more than, well, it's 4, negative 1 column-wise, and negative 3, 1 times 27, 34. When you multiply these out, you get the column vector 6, 7. And that's guaranteed to be the coordinate vector of the same vector v, but relative to the standard basis vector alpha. Okay, check it out. The original vector v is 27 times W1 plus 34 times W2, or 27 times 4x minus 1 plus 34 times W2, which was negative 3x plus 1. I'm verifying the claim that I found the coordinates of v with respect to alpha. Okay, well, if you multiply all this out, you get 108x minus 27 plus, or rather minus, 102x plus 34. And this gives us 6x plus 7. That's what v equals, 6x plus 7. That's what v equals, 6x plus 7. That's 6 times x plus 7 times 1. So what are the coordinates of v with respect to the simple basis alpha? They are 6 and 7. So the coordinate vector is 6, 7. Okay, that's what this change of basis vector does. Your author will call this the change of basis vector from alpha to beta, but it converts from beta to alpha. He calls it from alpha to beta. It converts from beta to alpha. I can't do anything about his choice of naming. Okay. So now what we're going to do is we're going to take about 5 or 10 minutes just to really get this formal. I've shown you how to construct the p vector. All I'm doing now is the general case. Okay, so we're looking at the definition of P, the change of basis matrix, change of basis matrix from alpha to beta, but which really, I'm just emphasizing this, changes from beta to alpha. Okay. All right. So let's consider two bases for the vector space V. So let alpha and beta be bases for V. Okay, so alpha will be, let's say, V1, V2, all the way up to Vn. Beta is W1, W2, all the way up to W sub what? Think about vector spaces. All vector spaces have the same number of elements in them. So if the dimension of this vector space is n, we will have n basis vectors in any basis. So we don't have different subscripts sub m. It's the same n. So we do this a very similar thing as we did when we were defining the matrix of T with respect to the bases alpha and beta. Very similar. We take each of the W vectors, the bases from beta, the basis beta, and we write them in terms of the basis alpha. So W1 we're going to write in terms of the V's, okay, which is not necessarily an easy thing to do, but not that rough, I guess. So we're going to call that P11 V1 plus P2 V2, but it's P21 because we're looking at W1, plus P31 V3 plus dot 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 plus Pn1 Vn. We do the same thing with W2. W2 is now P12 V1 plus P22 V2 plus P32 V3 plus dot 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 plus Pn2 Vn. And we do that with each and every W vector, and there are n of them, so we'll have Wn is now P1n. These are small p's, by the way. We designate the entire matrix we're looking for by capital P. These are small p's. So P1 and V1 plus P2 and V2 plus P3 and V3 plus Pn and Vn. Not Mn, it's Nn. And we have n vectors. Okay. And here's the vector. Here's the vector. Here's the change of basis matrix. You simply take the coordinates of W1 and put them in the first column. So P11, P21, all the way up to Pn1. We do that with W2, P12, P22, all the way up to Pn2. And we go to the last W sub n, P1 and P2 and dot 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 Pnn. Okay, and this is a square matrix, and this matrix converts from basis beta to basis alpha. So the most important results, of this, you already have them. I just want to emphasize. The first one, the coordinates of v with respect to alpha equal p times the coordinate vector of v relative to the basis beta. Okay, and p inverse converts the coordinates of a vector from alpha back to beta. Okay, so the second important result is the coordinates of v, the coordinate vector of v relative to the basis beta equals p inverse v alpha. Okay. Okay. Alrighty. I'm just taking a quick look at where we are. We're actually making good time here. Okay. So here's our final example, just to wrap everything up, to pull everything together. Okay. It's a bit of a long example, so bear with me here. So let's start out with the linear transformation. Let's start with a linear operator from P1 back into P1. So let T be an operator or linear transformation from P1 to P1 by T takes AX plus B and turns it into 2AX plus 3B. And consider the bases we did in the last example. Bases alpha and beta by the standard basis alpha, and the basis beta consisting of 4x minus 1 and negative 3x plus 1. Sorry about that. I wish I could get to just stop doing that. All right. And let's let v be a typical vector in P1. V equals 6x plus 7. Okay. I want to find T of v. I could do that immediately. All I have to do is put a equals 6, and I think b equals 7. I could find it immediately. But I want to find T of v by using the basis beta and computing the basis of, or the matrix of T with respect to the basis beta. Okay, that is, I want to compute T of v by finding its coordinates. The coordinates of T of v with respect to the basis beta are equals the matrix of T with respect to beta times the coordinates of v, coordinate vector of v relative to the basis beta. So first I want to find the coordinate vector of v with respect to beta. Okay, so first let's find the coordinates of v relative to the basis beta. Okay, so that means I need to take each of the vectors. That means I need to take the vector v and write it in terms of the basis vectors beta. Okay, let's do that. So v is 6x plus 7. Okay, and that's going to equal sum C1 times the first basis vector, 4x plus 1 plus C2 times negative 3x plus 1. This is old news for us. We don't even have to have linear transformations in the discussion to talk about this. Okay, this simply results in a system of equations. So the system of equations is 4C1 minus 3C2 equals 6, and negative C1, the constants, plus C2 equals 7. Okay, a very simple system to solve. In fact, I can just multiply the second equation, let's say, by 4. So I'll have 4c1 minus 3c2. I'm not even going to use Gauss-Jordan elimination method. I'm just going to multiply the second equation by 4, then add the two equations together. Okay, so plus 4c2 equals 28. Just multiply the second one by 4. Add them together, you get c2 equals 34. Okay. So c1 will equal c2 minus 7. So c1 equals c2 minus 7, which is 27. Okay. So therefore, the coordinate vector of v relative to the basis beta is just the column vector 27, 34. Okay, not the vector v, but the coordinate vector v, but relative to the basis vector beta. So next is where all the work comes in if we don't use that alternate path. Next, find, this is the tough part, the matrix of T with respect to beta. And by that, I mean directly, like we did in the last section, last video segment. Okay? That means I need to find T of each of the basis vectors in beta. So T of 4x minus 1. T of 4x minus 1 is 8x. Remember, our linear transformation is 2ax plus 3b. 2 times ax, 2 times a times x plus 3 times b. Okay, so that's 8x minus 3, sorry. And now we write that in terms of the basis beta vectors. Okay, so this is going to be a11 times the first beta vector plus a21 times the second beta vector, basis beta vector. Then I find T of the second basis beta vector, negative 3x plus 1. Find it directly. It is a negative 6x plus 3. And I'm just putting the coefficients of negative 3x plus 1 into the formula for the linear transformation. Remember, linear transformation above here, we forgot it, and let's say red, takes ax plus b, doubles a, multiplies that by x, so 2ax, and then triples b, so plus 3b. Doubles a, 2 times negative 3 is negative 6, and triples b, 3 times 1 is 3. And then we take that and write it in terms of the basis vectors, beta vectors. God, I hate doing it. It keeps doing that. So this is, oops, back to black. So a12, beta vector number 1, plus a22, beta vector number 2. And this is where all the hard work is. Each of these equations results in a system of equations. The first system will look like 4 a11, and then minus 3 a21 equals 8. Then the second equation will be negative a11. I'm looking at the first equation here for forming our first system. So plus a21 equals negative 3. The second equation also gets a system, a different system, but the same coefficient matrix. I hope this is familiar to you. So 4a12 minus 3a22 equals negative 6. And also negative a12 plus a22 equals 3. Okay, I have two systems, two separate systems, but the coefficient matrices for these systems are the same. So we can solve both of the systems simultaneously by producing that thing I called the super augmented matrix. So there's the coefficient matrix. If we were just solving the first system, we would look at 8 and negative 3. If we were just solving the second system, the constants would be negative 6 and 3. Since the coefficient matrices are the same, we use it once and apply the Gauss-Jordan elimination method to this super augmented matrix. We find the RREF, and I did this off camera. And I got negative 1, 3, negative 4, 6. Okay, so that tells us that that final matrix, or the right-hand part of that matrix, on the right-hand side of the dotted line, that's the matrix of T with respect to beta. Negative 1, 3, negative 4, 6. Not so much fun. And this is just by a 2 by 2 system, so this isn't so bad. Even though our calculators can compute this, there's a lot of work going on here. So the coordinates of T of V with respect to beta are, by our big result from last time, the matrix of T with respect to beta times the coordinate vector of V relative to the basis beta. Okay, or just writing it out. This would be, of course, we let our calculators do the actual multiplication. And in part A, we found that the coordinate vector was 27 and 34. 27 and 34. If we multiply this out, we get 75 and 96. That's the coordinate vector of T of V. So T of V itself has these coefficients of the basis vectors beta. So it's 75 times the first beta vector plus 96 times the second basis vector beta. And we get 12x plus 21. Okay, so this was the theoretical hard pathway, difficult pathway to finding the coordinates of T of V with respect to beta. And that was by finding the matrix of T directly. Part B, just to finish things up, is to do the alternate path. Okay, so form the matrix of T with respect to the basis beta by the, and I'll call it the alternate path. Okay, and what does that mean? I'm going to write it real big. The matrix of T with respect to beta is the inverse of the magic matrix times the easy T, matrix T with respect to alpha, times the magic matrix, where P, your author calls it the change of basis matrix from alpha to beta, but really it changes from beta to alpha. Okay. Okay. So let's do that. The first thing we need to find is the matrix of T with respect to alpha. Okay. Well, that means we need to find the action of T on each of the basis vectors. Okay, so T of X, well, I keep referring to T without writing it out. So here's a reminder up, just a little up here in yellow. T of AX plus B was 2AX plus 3B. So there it is. So Okay, so t of x is, well, in this case, a is 1 and b is 0. So t of x is 2x. And I got to write that in terms of the standard basis vectors. So this is 2 times x plus 0 times 1. That's so, see how simple that is to do with the standard basis vectors. I also need to take t of the second standard basis vector, t of 1. T of 1, I put in a equals 0 and b equals 1. It's just 3. And then write that in terms of the basis vectors in alpha. So this is 0 times x plus 3 times 1. So look at how fast. There's no super augmented matrix or anything else. Look at how fast we can find this simple matrix of t with respect to alpha, where alpha is the standard basis. We just take the coordinates of t of x, put them in a column, take the coordinates of t of 1, put them in the second column, and boom, there it is. No systems just to solve. And then we finish this off. The matrix of t with respect to beta is then p inverse times the matrix of t with respect to alpha times p. Well, we found p in the first example in this section. So this is, let's say p was 4, -1. We did this in an example earlier. -3 and 1. We take the inverse of that. We multiply it by the matrix of t with respect to alpha. And then we multiply it by p again. We don't do any of this by hand. You just have to enter these into your calculator or a computer or whatever and let the computer compute this. The matrix of t with respect to beta in one step on your graphing calculator or whatever. No systems to solve. The hardest thing was finding p, and that's not too bad. And this is the same matrix of t with respect to beta we found earlier. The matrix of t with respect to beta we found earlier was -1, 3, -4, 6. -1, 3, -4, 6. We don't need to finish the rest of the problem. We'd already, once we find the matrix of t with respect to beta, we're back to this stage right here. Earlier. Okay, so this ends the difficulty or the problem. Okay, so this ends the video segment. I'm gonna give a maybe 1 minute recap of everything in this section. You can stop the video now and go ahead and dig into homework if you don't want the recap. But this was a long section, so real quick recap. Every t from Rn, we started this full circle now to Rm, is given by t of x equals ax. And that's sweet. We would like every linear transformation to do this. We don't get that, but we get close. Every t from vector space V to vector space W is given by a similar, the coordinates of t of v with respect to beta equals sort of like ax, but instead of a we have the matrix of t with respect to the bases alpha and beta, and sort of like times x, but not quite, is the coordinates of v with respect to alpha. Okay. Often, very often, we consider a matrix going from V into V again. Okay, so the coordinates of T of V with respect to beta would equal the matrix of T with respect to beta times the coordinate vector of v relative to the basis beta. Okay. The matrix of t with respect to beta may be difficult. Might be difficult to compute. So we have an alternate path. Alternate path. The matrix of t with respect to beta equals P inverse. Matrix of t with respect to alpha, which could be easy to compute if alpha is the standard basis, times p. Okay, where p is called the change of basis matrix from alpha to beta, which converts from basis beta to basis alpha. Okay, and that's our summary. Okay, and that ends I think the most difficult section in our course. The upcoming sections they involve quite a bit of work, but not anything close to this. So we've gone over the peak, I think, in this course. And as usual, I'm looking forward to talking with all of you again very, very soon.